a spring with a constant of K equals 250 newtons per meter, that's the spring constant, is fixed to a frictionless inclined plane, okay, that makes an angle of 28 degrees, okay, with the horizontal. The relaxed length of the spring is L0, okay? So that means that at that point, at L0, the spring isn't exerting any force upward or downward. So quick sidebar, force equals K delta X for a spring, and the relaxed, what do they say? What is relaxed? The relaxed length is where delta X equals 0. So this is our 0 point right here. Okay, as shown in the figure to the left, a block of mass 2.8 kilograms, okay, right there, is attached to the spring. The new equilibrium length is 0.4. So equilibrium is different than relaxed length, because equilibrium means the mass is pulling this way, the spring is pulling that way, and the net force is 0. Acceleration, so net force equals 0, and that implies that acceleration will also equal 0, is 0.4, okay? As shown in the figure in the middle. How far does the spring stretch when the block is attached to it? Okay, so we're talking about how far so we have 0 that's right about there, and we have a delta x, which is about that distance right there. So we want to find out that delta x. So I know we already have a picture, but I'm going to redraw it because it helps me think, helps me visualize and intuitively understand things better when I redraw them. And sometimes it makes things clearer. Whoop. So we have a force going down this way. That's going to be force due to gravity. And then we're going to have a force going up this way. That's going to be force due to spring. And since they are in equilibrium, in this case what that means is that net force equals 0. So force gravity plus force spring will equal 0. One of them will be negative with the other, basically meaning they're acting in opposite directions. And so we can say that the force going down due to gravity, that's going to be mg sine of theta. So we have the block here. Scroll up a little bit. We're going to have mass times gravity. And then after we do some geometry, we could decompose this vector. This would be mg sine, I know, terrible writing. That's supposed to, and then perpendicular to that, we're going to have mg cosine of theta. Take the vector, decompose it into parts. The part that's sliding down, the force that's causing it to slide down the ramp, is the sine component. It's easier just to memorize sine sliding. So this will be Fg right here, will be mg sine of theta, as opposed to cosine, which will be the normal component. This will be cosine of theta, mg cosine theta. This is mg sine of theta. You can derive it using geometry. You might want to do that once, but it's tricky enough that you don't want to do it on a test because there's a good chance you'll make a mistake and it just takes too much time. Worth just memorizing. So mg sine theta equals, and I know my signs are going to get kind of funny here. I'm just going to basically ignore the signs and then make everything work. So mg sine theta will be k delta x, where this delta x here is specifically, I'm going to call this delta x1 maybe, implying that this is due to length L1. Yep. And normally, sometimes you'll see this being a negative there, saying that the force is opposite to the stretching of the spring. So we know everything here except delta x, which I'm going to rewrite delta x as k. Do they want delta x? Yep. This will be L1 minus L0. L1 minus L0. So that's the equilibrium, and that's the stretched portion that we have right there. I know, that may not actually spell stretched. So what we're searching for then, click, clack, clunk, is this guy. Rearranging it, we have L1 minus L0 equals mg sine theta all over k. Looks like an R, supposed to be a k. There we go. Yeah, I think that's pretty solid. Calculator on, clear. We're going to have to do a a sine. So we're going to go over to degrees, second quit. M is, I think it's 2.8. 2.8, yep. So we have 2.8 times gravity, which I'm going to say is 9.81. I'm going to multiply that by the sine of 28 degrees, which we already changed, which is good. Then we're going to divide that answer by 250, which I'm pretty sure 250 is the, yep, it's right there under all of my scribbling. 250 newtons per meter. Look at our answer. We get 0.05158. So 0.05158. See which answers we have that are possible. Yep, this one right here. So if we rounded that 5 to a 6, then it would be this answer right here. So our answer, get rid of some of this so we can focus. Focus. I guess zoom in. Enhance. L1 minus L0 is 0.0516. So that's the point of equilibrium where the mass of the block cancels out the force of the spring pulling it up. So these two forces, force gravity, force spring, are equal. Okay. The block is then pulled down the ramp further, probably like so, further stretching the spring to a length of 0.048, L2. Yep, got L2 right there, as illustrated in the image to the right. And released. As the block slides up and down the ramp, at what spring length will it be moving the fastest? And it'll keep going up and down forever because there's no friction really to lose that energy. So it has the energy due to the spring when it's stretched like this, then it comes up and has not only the spring pushing the block back down because it moves probably past this equilibrium point, but then it has gravity pulling it down too. So we're going to look at a few situations here. So I'm going to just redraw this. So we have the block all the way stretched. We have the block, oh, that is a tragic, okay, there we go. Block, we're going to say at equilibrium. So this will be L1. This will be search L2. And this would be something between L1 and probably L0, let's say. So what happens, interesting. I'm gonna say this is gonna be L0. It's just gonna intuitively look at this problem. You gotta be extra careful with these kind of problems because you have a lot of points for just a multiple choice question. So you really don't, it's really easy to make a mistake. So for this one, if we look at the forces, change it to blue. So we have force gravity, and then I'm going to draw a big force spring because we know it's very stretched. And the overall force will be that direction. Okay, so that L1 is where we have the equilibrium. Right. New equilibrium, L1, yep. And so that means that we're going to have a force spring going up, force gravity going down, and net force will equal 0. And then when we get a little bit higher, we will have force gravity pulling it down, but there'll be no net force from the spring. So force will be going this direction. And then when we get above the relaxed length for the spring, we're going to have force gravity and force spring going this way, and therefore we'll have a big force going that way. So what's going to happen here is this block is going to accelerate upward. It's going to stop accelerating at L1. Then it's going to start accelerating backwards, back down the ramp, past L1. Is that true? Yes. Because after it gets past this, the acceleration starts going downwards. We have a lot of downwards when we get to L0. And then once we get above L0, we get even more back downwards. So the way you're going to look at this is you want to have a maximum acceleration upward and minimum acceleration downward. So if we start here, we get get a building acceleration upward, and then right here, that's when our acceleration is cut off. So we maximize the amount of acceleration going up, and then as soon as we cross the point where we're no longer accelerating, that's going to be our maximum speed. So we're going to have a maximum speed here, and then the speed will start diminishing before it turns around. So L1 will be the point where it has the most speed upward. So at what length will it be moving the fastest? L1, right there. Yes, that is correct. And then just look at the other ones. So this is halfway between the two. So this is saying this is L2. And then like halfway between the two, that's what they're talking about with A. And then up here, we're talking about L0. That's going to be moving slower because it's spent at some point of time here decelerating. Okay, so that's the idea with how to find the fastest moving portion of the block. Now, what is the speed of the block when the spring's length is 0.35 meters? Okay, so we're going to look at two scenarios. So this block is moving up and down continuously. And so we want to pick 2 points and do kind of an energy balance type thing. So we have one point we know where it's not moving, and that's 0.48. Pull down to the ramp, further stretching the spring to 0.48. So we have the block at, this will be 0.48, and speed equals 0. I'm going to say delta x equals, and then here, delta x equals 0.35 meters, and v equals question mark. And we have a block here. So what we're going to have is we're going to have the same amount of energy in both scenarios. So if we look at the energy in the first one, we're going to have, because there's no way for it to lose energy. No friction. No way to lose energy. So for this, we're going to have energy potential at initial plus energy kinetic at initial, which will be 0, plus energy potential due to the spring. This one I'm going to say is due to gravity. This one will be due to the spring. So they're both energy potential, but I still want to differentiate them just for simplicity. Energy potential final plus energy kinetic final plus energy potential spring final. Yep, I'm good with that. And so now let's take a look at what each of these are. So energy potential, that's going to be due to height. And so I'm going to move this one over here and say, nope, I'm going to move this one over there because the block is moving up, so the energy potential final will be higher. So I'm just going to call this change in energy potential final. I'm going to say it starts at 0 at rest. And so energy kinetic is 1/2 mv squared. If this v is 0, then that whole thing is 0. We have energy potential to the spring. That's going to be 1/2 k delta x. And then delta x is going to be how much the string is stretched. I'm going to say from the relaxed length, I don't think it actually matters because you're trying to find the difference in energy here. But I'm going to say from L0 because that seems like a good baseline. So I'm going to call this, it's going to be kx squared. So it's going to be L2 minus L0 squared. And that takes care of that right down there. Energy potential final, we got that. This is plus 1/2 mv squared, but that's our mystery velocity. Plus, I'm going to do 1/2 k. Now this, we're going to have 1/2 kx squared again. But the idea here is we're going to use L of 35, right there, 0.35, minus L0. And then that'll be squared. Yep. And so, let's see. Yep. And we can find this value and we can find that value. So to do that, though, we're going to have to find L0. There might be a way of working this around without finding L0, but I think it's probably easier and simpler and intuitively makes more sense if you think of everything in terms of the relaxed length of the spring. So we have 0.0516 equals L1 minus L0. Rearranging, we have L0 equals L1 minus 0.0516. L0 equals, I'm just using our answer we got right here. And L1 is 0.4. So we have on 0.4 minus 0.0516. We get 0.3484. 0.3484. Okay? So L0 equals 0.04 03484. 03484. L35 equals 0.35. Yep. Wait a second. I think I have an extra 0 there. Yep, I have an extra 0 there. So this is 0.3484, which is almost 0.35. And then we have L, and due to the rounding, it might actually be exactly. I'm not sure. But I'm going to go with this one because that's kind of the answer key they gave us. And then L2 equals 0.48. L2 equals 0.48. 0.48. So now we have all our information. We know everything except that. So I'm going to solve for these real quick. So this value right here. So we do 0.35 minus second answer, and we have 0.0016, which when we square that, it's going to be very small. And then we have this one right here, which is 0.48 minus 0.3484, which is 0.1316. 0.1316. We also know K, which I think is 250. 250. Ooh. And we need to find this portion right here. I know, super messy. Super messy. I should be more organized. So energy potential is how far up the block has moved from one spot to another. And so if we redraw this as a triangle, this triangle will have a length of 0.48 minus 0.35. This will be theta, which is 28. And so to find the height that it moves up will be H, I'm going to call this H, equals sine of theta times 0.48 minus 0.35, little parentheses. So if you forgot what sine of theta is, SOHCAHTOA, opposite over hypotenuse. This problem is more involved than I had originally intended. So then we are already in degrees, which is good. So I can quit. So we'll do 0.48 minus 0.35 times sine of 28, 0.06, 0.06, 103. That's not a lot. It's a bit. 0.06, 103. Yeah, it seems okay. So that's the height. And so the potential energy, what I have energy potential there, change in energy potential final, will equal mass times gravity times height. Mass, I think, is 2.8. 2.8 times gravity times height. So we take that previous answer we have times 2.8 times 9.81. Perfect. 1.676. 1.676. Putting everything together now. So I'm going to rearrange it so we have 1/2 mv squared on its own. I know, so messy. So messy. I feel like I could make this cleaner, but part of me is also like, no, this is just kind of a messy problem. So first thing I'm going to do is I'm going to solve for, I'm pretty sure this will just be negligible. I can ignore it because it's like 100 times smaller than that. I should probably leave it in just in case. Okay, so we're going to have 1/2 k, nope, do it this way. L2 minus L0 squared minus 1/2 k L35 minus L0 squared minus 1/2 energy potential final. Nope, no 1/2 there, just energy potential final. I should probably put a delta there. That's so messy. I'll just say change in potential energy. Whoop, there we go. Delta energy potential. That's due to gravity. 4 terms, 3 on that side, 1 on that side. Yes. Okay, now we'll start calculating these out. So K is 250. So if we have, need to look at these real quick. All right, bigger over here. Make sure you get the calculator. Okay, put the calculator in the right spot. So we have 1/2, which is 0.5, times K, which is 250, times, now this is L2, so it's 0.1316, 0.1316 squared. That's going to be 2.1648, 2.146. Yep. And then for the next one, we're going to do 0.5 times 250, which is 125. I know, shortcut. Times L35 minus L0, it's 0.006, 0.0016 squared. That's going to be 3.2 times 10 to the negative fourth. 3.2 times 10 to the negative fourth minus, and then this one we already figured out right here, which is 1.676. This is 1/2 mv squared. V squared equals, At this point, I'm just going to ignore the 3. I could probably put it in real quick. 2.146 minus second answer minus 1.676. I know, it doesn't matter. That second part doesn't matter. Times 2 divided by 2.8, which is the mass. And so we get 0.3354. 0.3354. Okay? And now, the climactic finish, second square root, second answer, this should give us our speed. I know, so much effort. So much effort. 0.579. 0.579. This will be in meters per second. Okay, so let's take a look, see if that's a possible answer. 0.579. And maybe that one. I could have rounded something funny. Yep, I think I did this one correctly. So I'm going to say that that's just a rounding error. So the 0.579 really should be a little bit higher. And that the answer for this is 0.59 meters per second. It's pretty close. And I'm pretty confident with, despite the mess, it being the correct method. So to backtrack what happened, because we did a lot of craziness there. We had a spring on a block oscillating up and down. We were given an initial equilibrium for a rest. Then we attached a mass to it. It stretched a little bit, and we wanted to find out how much it stretched. That also kind of gave us a way of finding that L0 to start with. After that, we found out the spot where it's moving the fastest. Moving the fastest when it's accelerating for the longest period of time, but then stops. The acceleration basically switches from up to down. And you don't want to have any down acceleration. You do maximum upward acceleration, which is going to happen at point L1. And then we wanted to find out the speed at a specific spot. And that was just a energy balance, so to speak. Because when you hear the phrase speed, your first thought is, oh, energy, i.e. kinetic energy. Energy due to motion. And from there then, you can be like, all right, so we'll have an energy balance with the block on the bottom. At the bottom we have zero potential energy. And basically, we're going to say zero. Did we have zero potential energy? Maybe. Yes. So you have 0 potential energy at the bottom, moves up a little way, you gain some potential energy, i.e. you expended some of your energy, which you got from the spring, to raise the block up. You then also have kinetic energy, say it's at rest at the bottom, so 0 kinetic energy at the bottom, has some kinetic energy as it's moved up. And then you have energy potential energy due to the spring. In the spring, here it has lots of energy, here it has less energy. You write everything out, try and keep track of your algebra, and at the end you find out, well, okay, the amount of energy left over after the spring has pulled the block up and it's expended a certain amount of energy with the spring energy being 1/2 k delta x squared. You then find out that, all right, the final velocity is about 0.59 meters per second. So this is a fairly involved problem. Less conceptually difficult and more like a bookkeeping accounting difficult because it's easy to get your signs mixed up. As you can see, my advice in life is to draw a lot of pictures and try and solve it in as intuitive a manner as possible. Hope you enjoyed this. I will see you next time.